In this video, we're going to cover section 4.4 on Newman projections. And so up until this point, we spent most of our time discussing how to draw bond line structures for organic molecules. And we've introduced ways in which we can show some three-dimensionality using wedges and dashes. What the Newman projections provide is yet another way to view the three-dimensionality of a particular molecule. And we have to remind ourselves or cognizant of the fact that the single bonds in alkanes are constantly able to undergo rotations. And so as a result, alkanes can adopt a variety of possible 3D shapes. And we call these shapes conformations. And so we're going to use the Newman projection. We're going to show you how we draw Newman projections to better describe these various conformations that we observe for the alkanes. So the Newman projection is really yet another way to draw a alkane in this example and to show the three-dimensionality, the potential interaction of groups that are attached to neighboring carbons. And so we're going to use the Newman projection as a way to show the conformation of a molecule. So when we draw a Newman projection, you can see that it involves the drawing of a circle. This circle represents the carbon in back. And what I mean by that is that when we draw a Newman projection, we are focusing in on a single carbon-carbon bond. And the carbon in back is given this designation, the circle, and the carbon in front is the point to which these three bonds make with that particular carbon. So when you look at this Newman projection face on, this represents the carbon that is right in front of you, and behind that carbon is what we use. We use this circle to represent that. And so for ethane, which we know is C2H6, and this is our bond line structure, what we're doing is we're looking down this particular carbon-carbon bond. It's the only carbon-carbon bond in ethane. And so what's attached to this front carbon is 3 hydrogens. And what is attached to the carbon in back is also 3 hydrogens. And so this is one conformation for ethane, where you see we have the single carbon in front attached to 3 hydrogens, and the angles between those hydrogens is approximately 60 degrees. Pardon me, the angle between these two carbon-hydrogen bonds is 120 degrees. And what we show in back and attached to the outer edge of the circle are the 3 other hydrogens. So it's important to remember that when you're drawing your Newman projection, that the atom in front, you draw the lines directly to the center of that circle and they connect. And the atoms that are attached to the atom in back, in this case another carbon, are drawn to the outer edge of that circle. And so this is one conformation of ethane. And in future sections, section 4.5, we'll look at the various conformations of ethane. So let's look at an example of how we could convert a three-dimensional bond line structure to a Newman projection. So in this example, we have a dibromo, a 2,3-dibromobutane as our three-dimensional structure that we want to convert. And so the first thing we do is we need to identify which bond we're looking down. So the Newman projections are just going to show the arrangement of atoms around 2 particular carbon atoms. And so you can see in this example, we're looking down carbons 2 and 3. So we'll refer to this as the C2 for carbon 2, C3 bond axes. So that's important. You need to know from which perspective or angle, I guess, you are looking at that particular structure. So we're looking down the C2, C3 bond axes, so it's important for us to recognize what groups are attached to carbon 2 and carbon 3, and what is their three-dimensional arrangement around those particular carbon centers. So in the first step, you want to identify all the substituents, if you will, if you treat it as just a central carbon, what groups are attached to that carbon. And as you can see, we have a methyl group, a CH3 group. We have the bromine atom. Okay, so this is our first example of an alkyl halide. And what's not being shown in our bond line structure, which we normally would not, is the hydrogen attached to that carbon. So if these two bonds are in the plane and you have one group, this bromine atom, coming out towards you above the plane, then the hydrogen that's not being shown must be behind the plane. And so again, recall your tetrahedral that you'll always have for an sp3 hybridized center, two bonds that are in the plane, drawn as shown. You'll have a single bond that is above the plane, and then yet another bond that is below the plane. And so you have to remember that for an sp3 hybridized center, that you have that three-dimensional structure associated with the tetrahedral. So we have that tetrahedral in our first carbon, and we can identify the three groups attached to it: bromine, hydrogen, and a methyl group. Now, this is the way in which we would show that in our Newman projection. And I'm going to redraw the Newman projection. So we first start with our circle. I do it a little bit differently in the text, but start with our circle, and I'm going to draw the bonds representing those three groups attached to the first carbon. Now it's important to remember, just to notice that we're looking down this bond, and notice how in the plane we have this methyl group coming straight down. So if we're looking down the C2-C3 axis, this methyl group is below that axis, and it's in the same plane. And so we'll show that as a line straight down, and we will use CH3 to represent that group. Now the bromine atom in this structure is coming towards you. And so looking down the C2-C3 axes, that is the same, that translates into that bromine being on the right-hand side. Okay? And the hydrogen, as a result, will be on the left-hand side as you're looking down that C2-C3 bond axes. So this is the first part of the Newman projection. We've drawn the three groups that are attached to that first carbon, carbon 2 of our molecule. We have a methyl group below, bromine coming towards you, which when you're looking from the angle shown, places the bromine on the right-hand side and the hydrogen on the left-hand side. Now we can complete the structure for the back carbon, and you'll recognize that in back, we have the same three groups attached to the back carbon as we saw in the front carbon. So for the back, we have the methyl group really 180 degrees from the original methyl group on carbon 1. And so we can draw that in. And notice as I draw these methyl groups in, and I'm drawing the line directly to the carbon atom, not somewhere in the vicinity. I find that this structure is a little bit, unclear. It's very important to draw those lines directly to the carbon atoms to imply that, yes, it's a carbon-carbon bond that you're showing in your Newman projection. So if we continue, the bromine that is on the carbon in back, it is, again, above the page, and it will also be on the same side as that original, or the first bromine on the carbon in front, because they're both coming above the page. And so this bromine will be drawn on the same side, but now attached to the carbon in back, of course, is the other bromine. And the hydrogen will also be on the same side as the first carbon-hydrogen bond we drew on the front carbon. And so this is the Newman projection for this particular conformation. So this is one conformer of the 2,3-dibromobutane. Let's look at another example. So let's look at this example. This is a 2-methylpentane, and we're going to draw the Newman projection for 2-methylpentane with us viewing again a C2C3 axis. And I've drawn the what I call the spooky eye, looking down carbon 2, carbon 3. And so the carbon in front is carbon 2, and the carbon in back is carbon 3. So I'll start by, I like to start by drawing a circle to represent the carbon in back, and then identify the groups that are attached to the carbon in front. We have a methyl group that is straight down, and we have a methyl group that's coming towards us, which will be on our right. And what's not being shown is the hydrogen that will be to our left or in the back on our three-dimensional structure, but will be to the left on our Newman projection. So I'll first start by drawing the methyl group. Now there's a couple options for drawing methyl groups. You can draw the methyl group as we showed in the last example, but it's also acceptable to use an abbreviation, ME. And unlike when you draw the CH3 group, you don't have to specifically have the line to the M or to the E, just in the vicinity. So it's a little bit more forgiving. So I'll use that notation for this particular structure. So we have Me representing the methyl group. And what's also is our other methyl group, which will be to our right. And what's shown, or not shown in the bond-line structure, but we have to show in our Newman projection, is a hydrogen on the left. All right, so we have our first carbon completed. We have a methyl group straight down, a methyl group on the right, because it comes above the page and we're looking down the C2, C3 axis, and the hydrogen to the left, which is not shown in our bond-line structure. Now let's complete what's attached to the back carbon. So this is this carbon here. And so what's attached to this carbon is a C2CH3, that fragment of the molecule. So that'll be an ethyl group. And remaining, because there's 4 bonds to carbon and no formal charges being shown, we assume that there's 2 hydrogens attached to this carbon. So again, this methyl group is in the same plane as the ethyl group, and they are in opposite directions. So there's a 180-degree difference in the direction of those 2 groups. And so we can show that in our Newman projection. And thankfully for ethyl groups, there is also an abbreviation that we typically use. You can draw it this way, C2CH3 with the bond directly to the first carbon of the CH2 group, or you can use ET. So my preference is ET for clarity and space, but you can use the CH2CH3 as well. So an ethyl group is placed 180 degrees away from the original methyl group, or the methyl group on the first carbon. What's remaining are 2 hydrogens. And so this completes the Newman projection for this particular conformation of 2-methylpentane. So if you have any questions about drawing Newman projections, send me an email. We can set up a Zoom appointment or start a discussion in our forum. Thank you.